Okay, hi everyone. My name is Daniel Sun, and I am part of the Elementary Particle Experiment Machine Learning team at the UW in the Department of Physics. I am there doing research as an intern. And so the larger program that we're working on is applying machine learning to elementary particle experiments at the Large Hadron Collider. If you haven't heard of the Large Hadron Collider, it is the largest particle accelerator in the world, based in CERN, which is in Europe. All right, so this presentation is going to be split into several different parts, and you'll be able to see all the parts come together at the end. This here is a very famous picture in the world of particle physics. Essentially, what it is it's the decay products and jets of a proton-proton collision in the LHC that generated a Higgs boson. So you might have heard about the discovery of the Higgs boson. It was really big news a few years ago, and that happened at the LHC. And this is a photo representing that. We'll be talking about it in the next few slides. Let's start with the standard model. Particle physics is about, well, the study of elementary particles. This all comes the idea of particles originates from a Greek guy called Democritus, who came up with a thing called an atom. Basically, it was the whole question of asking, like, what is the smallest thing that exists that cannot be divided further? And back then, he hypothesized there's something called an atom that cannot be divided further, that everything was composed of. The atomic theory was proven to be, well, more or less correct by physicists. I think Brownian motion was one of the most convincing, one of the most compelling arguments for that. But then, upon further investigation, people found that, like the uh, standard atoms are consisting of protons, neutrons, and electrons. And then for a while, people thought, okay, maybe protons and neutrons must be the fundamental units. They must be elementary particles. It turns out that the electron is an elementary particle. As we know right now, it cannot be divided further into like smaller parts. It's not made of anything smaller. But the proton and neutron, turns out, are made of particles called quarks. The proton is made of two up quarks and one down quark, and the neutron is made of two down quarks and one up quark. This discovery of several quarks was in part fueled by particle accelerators, where the whole thing that happens in a particle accelerator is you take very small things, like you take clusters of protons or maybe ions, or in some cases, I think they use electrons, but that's very rare. And you use magnetic fields and stuff to accelerate it to an increasingly fast speed in a large ring typically. And if you take two things and then accelerate them to very fast speeds and then make them collide head on, you can generate some very, very exciting byproducts by that. Because the collision reactants have so much energy, that energy can be converted to mass, which then results in the creation of many new particles. And this can be used to study what these particles are made of. And all of this experimental evidence, as well as a nice theoretical framework, forms the standard model, which is, well, the model of particle physics today. It divides particles, the elementary particles, which are particles that cannot be divided into several classes. There's fermions and bosons. The difference between fermions and bosons is something called spin, which is kind of like its intrinsic angular momentum, but also a lot weirder than that. Bosons have integer spin, and they follow Bose-Einstein statistics. Fermions have half integer spin, which means that it's not an integer, but it's a multiple of 1/2, and it follows Fermi-Dirac statistics. The difference between these is that for fermions, it obeys the Pauli exclusion principle, which states that any two fermions cannot be on the same quantum state. You might have heard of this in your chemistry class when you're thinking about electrons filling into orbitals. Each orbital can only have a spin up electron and a spin down electron. You can't have two spin up electrons because then they would be on the same quantum state, and that is not allowed by the Pauli exclusion principle. One more definition to make here is, right, let's say quarks and leptons first. Leptons are usually a lot lighter than quarks. It's stuff like electrons and neutrinos, where quarks are particles that interact with the strong force, along with gluons. Now, quarks can't actually be isolated. Like you can't just have one up quark and isolate that because of a property called color confinement. But you can study pairs of quarks or multiples of quarks, and these particles are called hadrons. They're composite particles made of quarks that interact with a strong force. Hadrons make up most of the matter that surrounds us, like protons and neutrons are hadronic matter, for example. Yeah, okay. And hadrons is what are collided in the LHC. That's why it's termed Large Hadron Collider. Large
Daniel,
Hadron,
I just have a question about bosons in the last slide. You introduced the Higgs boson. Out of curiosity, do scientists know if they've discovered all the bosons yet?
actually, there's a hypothesized boson called the graviton. Now, why bosons are important in particle physics is that they're used to explain forces. Uh, the strong force is explained by the gluon. The electromagnetic force is explained by the photon. The weak force is explained by the W plus, W minus, and the Z bosons. However, we have no boson that can explain or that can adequately explain the force of gravity. That is why actually we're going to talk later. The standard model is now is considered incomplete. There's a lot of things that it can't explain, even though it does explain a lot of things very, very well. So that's why there's now searches beyond the standard model, such as the search for a graviton. So that's a good question. Now let's talk about the Large Hadron Collider. It is a very large particle accelerator that is 27 kilometers in circumference and sits on the border of two countries. It consists of a large ring with four detectors on it: Atlas, CMS, Alice, and LHC Beauty, or LHCb. I won't exactly talk about the specifics of each detector, but essentially what happens in the LHC is you collide proton clusters. You don't just collide one proton and another proton because that's too hard. You collide a whole bunch of protons with another whole bunch of protons. And through this, you can test various particle physics theories, such as beyond the standard models theories, supersymmetry, etc. It was notable when it received the 2013 Nobel Prize in Physics for the discovery of the Higgs boson. In the Large Hadron Collider, proton clusters will smash together, and once they smash, they form something called quark-gluon plasma in the interaction point. Now, it's perhaps too complicated to completely model what happens at this point, but if you think about this in terms of conservation of momentum and conservation of energy, remember that something that is very, very fast has very high energy, but if their momentums are assume we have like a proton cluster going to the right and another proton cluster going to the left and they collide. If we conserve momentum on the whole thing, it seems like the total momentum will be small because the momentums cancel out, but the total energy will be very, very large. Now, how does this resolve itself? By creating new particles. The energy goes into the form of mass. Now, we know from relativity that energy can be in the form of both mass and momentum, where, yeah, energy can be in the form of both mass and momentum. If originally most of the energy is in the form of the momentum of the two proton clusters, but once they collide, a lot of the energy gets converted to mass, and you create a lot of really fun particles from that. In the LHC, the typical energy scale is about 13 tera electron volts, where the electron volt is a unit That's the energy or the work required to move one electron through a potential of 1 volt. It's very often used in particle physics. The prefix tera means 10 to the, let's see, kilo, mega, giga, tera, 10 to the 12. So this is 13 times 10 to the 12 electron volts, which is a very, very large number. For reference, the mass of a electron is about 511 kilo electron volts, and the mass of a proton or a neutron is about 928 mega electron volts. Another remark to make here is that in particle physics, we set C is equal to 1. We have something called natural units. You'll see this if you study electromagnetism in Gaussian units and so on. If we choose a system of units such that the unit of length divided by the unit of time, like for example, 1 meter divided by 1 second, if we redefine the meter in the second, is exactly equal to the speed of light, then that makes our calculations a lot simpler because we can just drop c out of all of our expressions and we can just avoid having to write c all the time. So yeah, okay. Now after a collision, you get something called relativistic jets. And this is because of, really just due to the theory of special relativity, where because the protons that are coming in are moving so fast, all the products must come out, or all the products must come out in a cone with a very narrow angle because of relativistic velocity addition. It turns out that 50% of the radiation, even if it's light, must come out in an angle of theta equals 1 over gamma, where gamma is the relativistic factor. It's a parameter that depends on the speed of the protons. With the speed that the protons are going in the LHC, this turns out to be about 1.4 times 10 to the negative 4 radians. If you want to convert it to degrees, that's something like what is that? That's something like 4.5 times 10 to the negative 3 degrees. It's like 0.0045 degrees roughly. So because these particles come out, each kind of like distinct jet of particles come out in a very small angle, we call them jets. And you can kind of think of them as cones that are pointing away from the central point where the protons have collided. So initially you have 2 protons coming in on lines, and then all the products they produce after they like kind of explode at the center comes out in these cones called relativistic jets. All right, so that is the kind of the background from particle physics that you will need. Now we'll go into machine learning. This is a nice XKCD that actually pretty accurately describes what you do in machine learning. So I'm just going to read it real quick. Guy on the left says, this is your machine learning system. Yup, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. Now, stirring the pile is something called hyperparameter optimization, where you literally change around numbers. The best way to do this right now, pretty much the best way, is to randomly change around some numbers in your program until your program outputs something nice. And this is no joke. So let's start off by talking about linear regression. So you guys probably have heard of linear regression. Given a data set with a list of inputs x, each of which are like real numbers, corresponding to a list of inputs y, we want to find the line of best fit. And now if you, let's see, can I get a pointer? Oh well. If you take a look at the diagram on the right, look at the thing on the far upper left hand corner. It has a circle x sub 1 superscript 0 goes to y sub 1. You can kind of think of this as like linear regression. It makes sense, right? For each input x, we want our program to predict an output y. And how it does that in this case is each arrow corresponds to a linear function. So it's some weight m multiplied by the input plus some bias b. and this is just the equation for a line. So if we do linear regression on our data set with x and y, we can represent it with this diagram. But then we can generalize. For example, what if we have two input variables, x1 and x2, that get mapped to a y in a linear fashion? Well, then we can do the same thing where, again, each arrow over here represents, each arrow has a unique weight and a unique bias associated with it. So here, y1 would be equal to like uh, m1 x1 plus b1 plus m2 x2 plus b2. Or actually, in practice, the biases are all kind of collected together, but we don't. It's the same concepts. So we have m1 x1 plus b1 and then m2 x2 plus b2. Or we can have one input variable x predict the output for two output variables y, in which case, again, each arrow has its weight and its bias. Now, we can generalize even further. We can have multiple inputs and multiple outputs. And in this case, each arrow is still just a linear function. It's just m1 x1 plus b1, there's a unique weight and a unique bias associated with each arrow, but it's still just a linear combination of like the inputs forming the outputs. Now, uh, there's something that there's a problem with this though. If we have, let's say that we have a data set that doesn't follow a straight line, it follows some weird curvy line. Let's say it's a quadratic, for example. Then our algorithm can't, or we can't model that with just a linear, with just a linear relationship. So what do? We introduce non-linearity. The problem is that even in this case, we can imagine stacking multiple layers, like stacking multiple of these um, layers on top of one another, right? For example, x1, x2, x3 goes to y1, y2, y3, but we can have another layer over here and we can have it output like z1, z2, and z3, where y1, y2, y3 is just an intermediate layer. Then essentially we have a black box where the inputs are x1, x2, and x3, and the outputs are z1, z2, and z3. There's a problem with this. Multiple linear layers in a row is mathematically equivalent to just having a single linear layer. You can't add more complexity by adding new layers. The solution to this is to introduce nonlinearity. And what we do with this is that we add what's termed an activation function at the end of each of these layers. So instead of saying that each arrow is just mx plus b, first we calculate mx plus b, then we take that value and apply a nonlinearity to it. And the list of nonlinearities is on the right. So another way to think about this is we compose one of these nonlinear functions with our linear function. So you take the output of our linear function and you input it to one of these functions. A really popular one is called ReLU. It's the second from the bottom. Another popular one is where for binary classification is the sigmoid. That's the fourth one from the bottom, as well as the tanh function, which is the third one from the bottom. You can see all of these are kind of complicated, like they're not linear, except for the linear one, which we don't use. So looking at this, now if we compose multiple layers together, we can learn additional complexity the more layers that we compose. And that's the whole idea behind neural networks. By using multiple of these layers and introducing these nonlinearities, we can make a network that can have enough complexity to map an input that it is capable of mapping an input to an output. Of course, we have to learn the network parameters, which are these weights. Like each arrow, remember, is associated with its own m and its own b. We have to learn these weights. And so the way that I typically like thinking about these networks is that it's some kind of black box with a bunch of parameters inside. It's some kind of function with a bunch of parameters, but the function takes in the input and eventually outputs like whatever your output wants to be. So how do we figure out the parameters? This would be incredibly hard, incredibly difficult to do with traditional methods, but the key to making this work in machine learning is a technique called gradient descent. We define a loss or an objective function of the network parameters. So it's a function of the network parameters that the network aims to minimize. For example, a common way to define the loss for supervised learning is to say, okay, if our network is a function f of x, where x is the input and f of x is like the output, then if we want the output to be, let's say we want the output to be 1, then a naive way to define the loss would be 1 minus f of x. Then the farther away f of x is from 1, or like at least like the lower it is, then the greater the 1 minus f of x will be, right? Or let's say we want the output to be 0, then we define the loss to be f of x. Then the farther it is from 0, the greater it will be. And so that means that we can mathematically write down a loss function that we want the network to minimize. And if the loss function, you can think of it as a function of the parameters, right? Here's a conceptual graph to help you visualize what's going on. Let's say that we have two parameters in our network. One is this x-axis and the other one is this y-axis. And the z-axis is the loss function. We want our network to find the minimum of the loss function. So we want it to walk downhill, basically. If you think of this as a topology now, we want it, or sorry, a topography now. We want it to walk downhill until it finds the bottom of a valley, and hopefully the bottom of the deepest valley that there is. And now what helps us with this is something called gradient descent. By using a technique called back propagation, the network can calculate at least locally, based on where you are, it can look around and find out which direction is downhill. And then after you find that, you take a step in that direction. And then you repeat. You say, which direction is downhill now? And then you take a step in that direction. And then which direction is downhill now? And then you take a step in that direction. This is the most naive form of gradient descent. And there's a lot of other techniques that machine learning engineers have developed to make this better, but this is a main idea behind it, where each step, which is usually called an epoch or an epoch, each step, you take a step downhill. And if you keep running this for a long time, the idea is you will converge, you'll like be at the bottom of the hill at the end. And so here's an example of kind of putting this whole thing together in action. This is called a dense neural network. This is the simplest kind of neural network. And this particular example is for binary classification. Notice that our input layer has a certain number of features, and then it has a bunch of arrows. This is a fully connected network. It has a bunch of arrows going to the nodes of the next layer. Now, remember, each of these arrows is a linear function compounded with a nonlinear function, where the nonlinear function is written above the second layer. Here it's ReLU. So we have already a lot of complexity. And then you have an even deeper layer. So you have more complexity and more complexity and more complexity. And then finally, in this final layer, we have a single node with a sigmoid activation. If you look back to what the sigmoid activation looks like, it only goes between 0 and 1. You might have seen this curve if you studied like population growth in biology. This is, or even the spread of the novel coronavirus. This is what people use to model is. The horizontal asymptotes are 0 on the left-hand side and 1 on the right-hand side, which means that the output of a sigmoid is always between 0 and 1. This is why this is useful for binary classification. If it's always between 0 and 1, then what the network outputs is kind of its percent confidence of how much it thinks. Like it answers a yes/no question, right? The yes/no question might be, given these inputs, is it a blank? Then the network is supposed to output a percent confidence of whether the answer is yes. So this can be generalized further, and we're just going to go over these very briefly, not really in detail, but just to give you an idea of what's out there. You have more sophisticated structures than DNNs that utilize known symmetries in the data. For example, spatial symmetry. This is the motivation behind something called convolutional neural network, where instead of using just a linear function mx plus b, you use something called a convolution. What a convolution is it's like you can kind of think of it as a sum of all the pixels in this square that's depicted over here. Hopefully you can see my mouse. It's all the pixels in this. It's kind of like a weighted sum of all the pixels in that square. And then you take that square and you scan it across the whole image, like row by row, and then all the columns as well, to get your next layer. Of course, with some kind of nonlinear activation as well. And you stack these layers together. The whole point behind these deep neural networks is that you stack layers together in a deep fashion. And there's several techniques that you can use and finally create some output. This is an example of multi-class classification because notice the output is actually 10 numbers. So we might say, okay, given an image, classify it into one of 10 classes. Like, is it a cow? Is it a what else is there? Is it a cow? Is it a cat? Is it a dog? Is it a whatever? You can have 10 classes, and what your network outputs is the percent confidence for each category. Like maybe it says this is 92% a cat and 5% a dog and etc. And the last kind of network we're going to be just briefly going over is something called a recurrent neural network. This is used for time series data or sequential data, like natural language processing or speech recognition. And the architecture of this is a little bit harder to explain, but it's just an example of there's many types of machine learning architectures that are very specialized for doing a specific classification task. Now, something that we've been doing in my team before our last project was working on jet classification at the OHC. That is, given low-level features, which are the form momentum of constituent hadrons. What this means is that, remember those jets we were talking about? The jet actually consists of a lot of individual particles, right? It's just they're all organized into a cone because of the ultra-relativistic nature of the decay. So if we look at each of these particles, the detectors at the LHC can record its form momentum. Form momentum is simply relativity lingo for its energy and its linear momentum. So we have a bunch of energies and linear momentums for the constituent particles of a jet. Using these, we can calculate some high-level features, where low-level features are the properties of the individual particles. High-level features are the properties of the entire jet that they're a part of. And using these features, we can construct physics-motivated architectures to have the input be like these, for example, these low-level features, and the output will be a multi-class classification, which tells us what kind of particle that this jet originated from. What's pictured on the right is an architecture that I worked on. Of course, I didn't create this one, but I implemented it, called a Lorentz boost network. It takes your input vectors, which are your input low-level features, and then it does what's called a Lorentz boost, which is a special relativity motivated machine learning architecture. And after a bunch of layers, it gets fed into a traditional dense neural network and finally outputs what class it's supposed to be. Now, all right, do we have any questions right now?
I mean, uh, they're not directly, they're more related to what you were covering in the beginning, but I just had a few questions about the activation network. So you talked about like ReLU, sigmoid, the different types. Out of curiosity, since there are so many types, do people tend to choose the activation function like based on the task at hand, since like multiple of them can serve the same purpose? Like, is it like trial and error, or like is there a systematic approach to choosing the optimal activation function?
That's a good question. So for the output layer, the convention is to use sigmoid for binary classification, and again for the output layer is convention to use something called softmax, which is um, not actually pictured here, but something called softmax for multi-class classification for the last layer. It's also pretty much industry standard right now to use, or at least it was industry standard a few years ago when which is where a lot of my sources are from, to use the ReLU activation function, which is the second from the bottom for all of your other layers. However, there are some exceptions. For a generative adversarial network, which we'll cover in part 3, ReLU is a bad idea. And it turns out that for that, you want to use something called a leaky ReLU, which is just kind of a modified ReLU. So to answer that question, there are loose guidelines for what kind of activation you should use in each step. But to actually optimize, you basically have to try them all. But the good thing is people have already tried them for a lot of architectures. So you simply have to look at the paper and find out what you're supposed to use. All right. Whoops. All right. And before we move on to generative adversarial networks, do we have any other questions? All right, cool. So let's let's talk about what a generative adversarial network is. First of all, it's a type of generative model. So what its purpose is to learn how to generate samples that look like they're pulled from a data set. And kind of what it does is pictured on the right. On the right is a GIF that shows how or the learning sequence of a generative adversarial network as it learns to replicate handwritten digits. So it starts from noise, and then very quickly it converges on, being able to generate something that actually looks like a bunch of handwritten digits. And this has been quite controversially known because it's good at making deep fakes. And I'm sure you've seen those videos of like on YouTube of people applying it to Obama's face because there's so many samples of Obama talking and making him say silly things, like maybe, yeah, just like making him say silly things. And so there's actually a lot of controversy surrounding this because as generative adversarial networks get better, you can make people say things that they've never said and then like post it to, I don't know, like Facebook or the news or something like that. So this is like it's an area of active research of both how to make generative adversarial networks better, as well as how to detect if something was generated versus if it was real. And this image over here, I believe some of these are real and some of them are generated, but honestly, I can't tell the difference. Like maybe the one on the lower right is generated because it's a little bit blurry, but I don't know. It looks pretty legit to me. Now, generative adversarial networks are completely unsupervised learning. What does this mean? In machine learning, algorithms are classified, well, mainly into two categories, supervised and unsupervised. There's also weakly supervised, but we won't worry about that. For supervised learning, you have a list of inputs and outputs. Sorry, yeah, you have a list of inputs, but you also have a list of outputs that you feed to your machine learning system. So essentially, you show your machine learning system each input at a time. You make it guess like what the output should be, and then you condition it based on what the output actually was. And so this means that you have an array of labels with which you are supervising your network. Generative adversarial networks are completely unsupervised. The only input to the network is the list of data that you want to try and replicate. So for example, a list of pictures of Obama, or a list of, in our case, a list of maybe some other kind of data. From this, completely unsupervised, your network will learn to generate the data. And now what does it do? It doesn't just like pull direct samples from the data, because that would be cheating. Instead, it learns from the ground up how to generate samples that look like they could be, look almost identical to something that's pulled from the actual data. So what happens in this is that we have two players in the game. We have the generator, whose task is to learn a function from noise to the data space. So given noise, you must construct some fake data. Then we give the discriminator the real data and the fake data, and we ask the discriminator to discriminate between them. So we ask the discriminator to say, look at these two samples. Which one do you think is real data and which one do you think is fake data? At the end, the objective is to have the generator completely fool the discriminator. That is, if the generator learns to generate pictures or data that is completely like the discriminator can't tell the difference between the generator's generated pictures and the actual pictures from the data set, well, then the generator is doing a great job, right? So that should be what this model converges to. And this is completely unsupervised, which is really cool. So to do this, let's play a game. For this, I'll need two volunteers. One person will be the generator and one person will be the discriminator. So who wants to, um, I can't even bring up my chat for some reason. Here it is. So who wants to be each? By the way, the generator task is probably harder than the discriminator task for the activity that I've set up. So I'll need two volunteers for this.
I can be the discriminator, I guess.
All right, so Tia's the discriminator and
I can be a generator.
cool. So Ashray is our. I hope I identified that right because I couldn't see the participant list.
Yeah.
Okay,
It's
Ashray is the
Ashray.
generator and Tia is the discriminator. Here are the rules. Our data is the format of our data is an ordered sequence of two integers from 1 to 100 inclusive. So here are some examples of data: 1, 2, 9, 8, 17, 9, 100, 1, and it's ordered. So that means that 1, 100 is different from 100, 1. Also, it has to be an integer, and it has to be both numbers have to be in the range 1 to 100. The numbers can be the same. For example, 8, 8 is an example of valid data. So what will happen is that each turn or each epoch, the generator will generate a sequence. So how this will work is that you'll DM me a sequence through the Zoom chat box. Then the discriminator will then I'll give the discriminator two sequences. I'll give the discriminator one sequence that was from the real data and another sequence that the generator has generated. Then the discriminator should give a percent confidence of which one is which. Then I tell you whether or not the discriminator was successful in telling them apart. So at the beginning, neither the generator nor the discriminator have any idea what the real data looks like. By the way, I've constructed the real data such that it follows a simple rule. So there is a difference that you can easily tell, like if you know the rule, but you don't know the rule. So at the end, you'll get feedback for whether the discriminator was successful or not. Pretty soon, the discriminator will converge first in this case. So the discriminator should figure out what the pattern is first, and then the generator has to basically try and guess it. And how the generator will do this is that the generator will generate sequences until the discriminator says 50-50. Because if the discriminator says 50-50, that means that the generator has generated something that matches the distribution of the actual data. So that's just kind of a hint for both players. And another thing is at the end, essentially what we're trying to train is the generator. We're trying to get a generator that can learn to generate fake data that matches the real data. All right, so let's.
Wait, hang on, David. You said that it ends when I say that I'm 50-50% sure, because that means that the generator has done a good job, right?
It ends when the generator can consistently make you say 50-50.
Right, but at the beginning, wouldn't I be 50% sure because I don't know the pattern either?
Well, yeah, but you'll see. You'll
Oh.
probably begin to see a pattern after like the second or third epoch, I'm guessing. So
Alright.
yeah, so you guys can all see this spreadsheet now, right?
Yeah.
All right, I'll be working in another spreadsheet and you'll be seeing values update as well as a chart of the discriminator performance versus generator performance as we go on.
Okay.
So with that, where's my Zoom chat box? Why doesn't it come up? Okay, here it is. With that, let's begin. So the generator, that's Ashray. Can you give me a sequence of 2 numbers that follows the general data rules?
1, 2.
All right, try again, but you have to DM it to me because remember,
Oh, okay.
Tia
Yeah.
can't know whether or not, like she can't know beforehand which one came from what. Okay, and so Tia, I'm gonna send you these 2 sequences and
Do I just read out the one I think is correct?
yeah, you could give a percent confidence. Which one do you, but basically, give me a percent confidence. Which one do you think was Ashray's?
I'm 50% confident that
Okay.
the first one was Oshray's.
Let's see. That's correct. The first one was Ashray's.
Incredible.
All right, so Ashray, give me 2 more numbers. All right. What about now?
I'm like 70% confident that the first one was Oshray's again.
That is correct. Let's see. That's all right. Ashray, I need 2 more numbers. By Vishnu. Bruh. All right. Which one do you think is Ashray's?
I'm 80% sure that the first one is Oshray's again.
All right, you are correct. All right, Ashray, you want to go again? Oh, by the way, the order in which I'm giving the numbers to Tia is randomized. I have a list of random bits that determines that. All right, so which one do you think is Ashray's?
The second one, I'm like 85% sure.
All right, you're correct again. Ashray, come on, step up your game. Ooh. All right, here are your next 2 numbers.
100% sure that the first one is Oshray's.
They're 100% sure the first one is Ashray's, but that is incorrect.
Oh.
In
Oh
fact,
no.
the second one was Ashray's.
Oh no.
All right.
Uh, 80% sure that the first one was Oshray's. I got the last one wrong because I can't do math.
Let's see. You're 80% sure the first one is Ashray's.
Yes.
That is, unfortunately, is incorrect. Whoops. Wait, what did I break? What? Why is that saying num? Well, whatever. Let's see. That's incorrect. In fact, 1020 was Ashray's. Why did it say num? Maybe I need to make this like 1e minus 5. Okay. So here are your next 2 numbers.
50% sure that the first one's Oshray's.
Interesting. All right. 2 more numbers.
50% sure that the second one's Oshray's.
That is correct, but since it's 50-50, All right, Asher, you want to give us 2 more numbers? Okay. Here are your 2 numbers.
50% sure that the first one's Oshray's.
Okay, and let's just do 1 more turn for fun. Okay. So 1 more turn for fun, and then we'll call it.
50% sure the first one's Oshray's.
All right, so the model has converged. What did he say again? Right. Actually, the second one was Ashray's. So the model has converged at this point, which means that now the generator has learned to generate data that matches the distribution of the real data, which actually, I have no idea how this happened, but the generator basically figured out the pattern right from the start. Like the pattern was just the second number is twice the first number, and almost like you guys can see from the column on the left that Ashray has only been giving me numbers that were the second one is twice the first. So this doesn't typically happen, but I guess it's fine because eventually you can see that the discriminator fluctuates for a while. But eventually by epoch number 7, the discriminator has learned like the discriminator has learned what the thing is. So let me extend this down actually, and then so eventually the discriminator has learned what the rule is as well. But since the generator also knows the rule and somehow knew the rule from the very, very beginning, how did you know the rule from the very, very beginning, or did you just guess? Dang. Okay. Because of this, now we have a generator that, without any other information to know whether like what the real data is, we have a generator that can convincingly generate real data. So on the right hand side is a graph of the performance of both the generator and a discriminator. You'll see that, of course, this is really simplified, but after some fluctuation, both have converged to a single value. And so we can declare this a success. All right, let's go back to the PowerPoint. Now you can think of what happens if the data is, instead of an ordered sequence of 2 integers from 1 to 100, if it's an ordered sequence of like 100 pixels from each one with an RGB value, which is 24 bits, then that's going to be a lot more complex. But we can use the same idea, the same architecture, basically, to train the generator and discriminator to learn how to generate data that comes from an input distribution. So what do we use this for? Well, what my team is currently doing is we're using this for anomaly detection. And what anomaly detection is it's saying, given a data set, it's basically trying to detect an outlier, right? So in this case here, let's make a scatter plot of 2 features of an aircraft engine, the heat generated and the vibration intensity. You can see that there's a big cluster in the middle, but if our new engine is, let's say our new engine is the green check mark that's like in the middle here, the one that's labeled okay. Because it's in the middle of this cluster, it's likely to be okay. But if we have a new engine that falls outside of this cluster, then it's likely to be an anomaly. Anomaly detection is trying to detect these anomalies. Of course, your actual distribution looks a lot more complicated. So here's the motivation for anomaly detection. By the way, pictured on the right is a brain. It is a concept that arises from string theory. Now, beyond the standard model, there's a few problems with the standard model. Even though it's so good at explaining so many things in particle physics, it doesn't fully explain why is there more matter than antimatter in the universe. How does gravity work, especially within the framework of general relativity? For example, is there a graviton? So far, there have been no experimental detections of the graviton. What is dark energy and dark matter? These are problems that arise from cosmology. Why do neutrinos oscillate in flavor? And why do neutrinos have non-zero mass? If you remember from the picture of the standard model, the neutrinos are the three things on the bottom here. They have non-zero mass, and they can do something called flavor oscillation, which is really cool. Basically, the neutrino can kind of spontaneously like change into a different form. Like if I have an electron neutrino flying through space, a short time later it could turn into a tau neutrino, and then it could turn into a muon neutrino, and then it could turn back into a tau neutrino, and then maybe back into a muon neutrino, and then back into an electron neutrino. That's called flavor oscillation, and that is something that the standard model does not quite explain. So we at the LHCO 2020, which stands for LHC Olympics 2020, it's an anomaly detection competition basically, where given a set of like dijet events, which are events with two jets, as you can kind of see in this diagram, right? There's the red jet and the green jet, which are going out in opposite directions. Given these two jets, which like try and detect if there are any anomalies. And how this works is that there's a W prime, let's say a hypothetical W prime boson that decays into a hypothetical X boson and a hypothetical Y boson. And we're given the information for all the stuff that comes out of this. And we're also given a lot of background, which is like maybe two jets that don't come from a W prime. And so we have a bunch of data, and we have no way of telling if there's any W prime in this data. So what do? We do anomaly detection. Here's what we do. We take all of our events and we kind of graph it with respect to MJJ, which is the invariant mass of both the jets. Here, we know for the purposes of research and development of our anomaly detection algorithm that it centers on 3.5 TeV. So that means that if we look like less than 3.3 and greater than 3.7 TeV, then we're likely not to find any of this guy, right? Because this guy centers on 3.5 TeV. So if we look at those regions, we can learn a generative adversarial network to learn the various features, like various high-level features of the two jets, and then interpolate them into the signal region. That means that we learn the generative adversarial network, and then we ask it, all right, now that you know what happens less than 3.3 TeV and greater than 3.7 TeV, what do you think happens between 3.3 and 3.7 TeV? And then it will give us a distribution. Then we can look for differences between the distribution that our generative model generated and the actual distribution. Because if there's a difference between the actual distribution and then the distribution that our GAN learned to generate, then, well, that could be the sign of the signal. That could be the sign that there exists some like anomaly in the region 3.3 to 3.7 that's not in the region less than 3.3 and not in the region greater than 3.7. So this is an area of active research by a team that I'm part of at the University of Washington. And yeah, so this kind of ties together everything that we've learned throughout the whole lesson today. And I hope that you learned something and that you think that this is as cool as I think it is. Do we have any questions before we wrap up the presentation? All right, cool. So yeah, I guess that's it. So we'll wrap up the meeting and I'll wrap up the recording for today. Thank you guys so much for listening to the end if you're watching the recording. And thanks everyone in the meeting for listening to the talk as well. All right.